So this is the next contribution, December 10th, and we will start to talk first about the Shannon Sampling theorem. Okay, we see, you see probably still the screen from a numerical experiment which I was doing with the STX program and a sound produced by MATLAB. So maybe it's a good idea to show you roughly, very roughly and very quickly what this program was. And so it's to your left. And so what I'm doing here is essentially I'm loading a frequency scale. And if I remember correctly, this was taken just from, I don't know, Wikipedia or some other demo, which says that there are certain basic frequencies of the piano, so to say, or the ordinary C major or so. And then I was using essentially Henning windows of length 496. So this is 2 to the 12, which is about the length of a tenth of a second to produce these things. And so what you also see here is that I apparently produce 49 sound elements. And these are frequency windows, and I'm producing them by doing a rotation and a modulation, which means that I'm taking this window and choose the kind of frequency terms going up and down, and then I'm essentially concatenating it one after the other and playing it with some short pause, and that's actually all. So you see it's very easy once you have typed in and saved the frequency scales or so. Now, I have already mentioned at the very beginning that the frequency of 44,100 samples is chosen because we want to store all the information up to 20 kilohertz, and 20 kilohertz, a sine or cosine of 20 kilohertz has 40,000 samples per second. That means if you would sample at a rate of 40,000, you might sample the maximal frequency without getting anything, meaning getting only zero. The fact that you can get something complete reconstruction if you have just 10% more, so 44,100 is a very nice integer number, which has a prime factorization of the form 2 times 3 times 5 times 7 squared. But it's also about 10% more than 40,000, so that you can reconstruct is the content of the Shannon Sampling theorem. And this Shannon Sampling theorem says that you can reconstruct a function in L2 from the samples if the sampling is taken below or faster than the Nyquest rate. What does it mean? Well, if the function is band limited, it doesn't contain too high frequency, which means it cannot oscillate too fast. And the Nyquest rate is essentially the maximal frequency. And if you know that the maximal frequency, let's say, is 20, then you can say that means you're having a frequency scale from -20 to +20. In our discrete MATLAB world, we would say it's a space of trigonometric polynomials of dimension 41. So if you're regular sampling along a divisor of your single length, that's why I choose 480. If that has more than 21 samples, you should have a chance to recover the function. Now, what I'm first showing here is just that that's just to fill in, this is a Gauss function, which is invariant, but if you're starting with a Shah distribution or a Dirac comb, and here this Dirac comb is chosen at the distance of 10, of course 10 divides 480, then you will see that its Fourier transform is having also the exactly 10 non-zero coefficients. So everything is zero and the rest is, and there you have to know, why do you see 2.2 or so? Well, because I choose in this representation the unitary Fourier transform. So it would be better to say, well, clearly here I have 480 signal lengths. So if I have at a distance 10, I have 48 would be the expected amplitude here. But we are taking the unitary version of the Fourier transform, which means we divide by the square root of 480, which is around 22. And then, of course, 48 by 22 is roughly speaking what you have here. Now, what is a band-limited function and how do I create a band-limited function? Well, very easily, I take a very, very smooth function with a very small density. So let's keep the idea that if I have so many samples, then I could take a larger spectrum, but here I take a few coefficients which are around 0. Yeah, you see here I've chosen maximal frequency 6, which is quite modest, and the function is therefore a linear combination, a random linear combination in a 13-dimensional space. Just to run it once more. No, it's yeah, okay, so it's okay, it's calling a fixed thing. So now if I go from here to the sampled version, I'm exactly multiplying with this Dirac comp. So multiplying the original function with this gives me a function which is 0 except coordinate number 1, 11, 21 or so. Remember 0 in my plot is first MATLAB coordinate. Now, since we have seen that multiplication goes to convolution, we can expect that now multiplication with this Dirac comp should go in convolution with the Dirac comp. But the Dirac comp itself is a linear combination of Dirac measures, and the Dirac measure applied as a convolution operator does a shift operator. So we have exactly this shape, you see it's constant shape, repeated along the position of this Dirac comp, which means we get 10 copies. And so if you see this information and you say, well, I was starting with this, somebody was sampling, I can translate with the FFT this information into this, how can I get back to this one? And of course, you look at the frequency domain, you would say, well, I just have to recover from this guy to this here. And how do you do it? You cut out the central part and you try to suppress the people, the things below. So I could do it with the Shannon Sampling theorem and just apply it, which would mean I would take a rectangular filter here. So I would do the ideal low pass filter. So in this case, I could multiply my frequency if I would know the maximal frequency is 6 with the filter symmetric of signal length n and maximal frequency 6. I multiply the FFT by this, and then I go back and I would recover this. More or less, this is what I was doing here. And of course, you shouldn't see any difference because the numerical error is at the precision level of our MATLAB tool. Now, yeah, this is done in a different way. So if you do it globally, you don't see a difference, but if you're looking at the reconstruction, now using the correct rectangular filter, not the correct, the ideal, which you find in the books or in mathematical descriptions, or you multiply with something like this. So I think there is some plot missing, but yeah, you can imagine if you multiply with this, which has a plateau reproducing the inner part and its slope, so it's having a plateau here and it's going down here. So, okay, so what is the difference? Well, we know that now that we are doing multiplication on the Fourier transform side, we should think of convolution on the time side. And the inverse Fourier transform, that's why I'm doing this comparison again, is this function, which is known to be a dilated version of the sinc function. Remember that this guy here is fairly thin and small, therefore this will be an even more broad Gauss function, sinc function, very, very flat and poorly decaying. And of course, because we are in a discrete setting, it's a finite discrete Gauss function. And here it's a little bit more smooth, and therefore it is much better concentrated. So essentially, how did I get such a function? Well, I took a somewhat broader rectangular function, so a broader filter, and then I was convolving it, which means smearing it out with a small bump function. I'm not sure exactly what I was doing here, but probably I was like taking a broader plateau function and then convolving it with 2 or 3 more narrow, maybe more smooth bump function. But the point is, this is smooth. Therefore, smoothing it out means compressing here, removing the high frequency part. So here you see in a direct comparison how much better these these functions are applied. And now the Shannon sampling theorem says, well, we have to convolve this discrete version with either the green or the red guy. And of course, green is our favorite. And what does it mean? That you put any of this collection, so at every sampling point you have now a copy of the red guy here, and you see how much they're overlapping. Or you're taking a guy from the green collection, which are much better concentrated. You see they have negative terms a little bit, both of them actually, but the amount of overlapping is much more visible here. So what is the benefit of having a better concentration? Well, very often in real life, so to say, you have not all the data, and if you want to reconstruct by, let's say the CD player or streaming portal is providing data, you don't want to record it first, then compute the sound and then play it afterwards. You want to do it as you go. So you might have a few samples from the future part, but not all of them. And therefore, when you look at the error that you get by reconstructing only locally, that means I'm using either only the samples in the middle segment. So maybe I should mark them, or I cut out here and I say, well, I'm reconstructing from a local part of this, or and I have no further information at the boundaries. And then I would say, well, now let's look at the reconstruction, actually at the reconstruction error. Now there's a typo, it should be sync basis. And what you see here is there are still big oscillations. Why do you have these big oscillations? Well, they would be canceled out. So in the perfect reconstruction, you add all of them and you cannot distinguish the whole reconstruction. But here you see much better how they are, how the future and the previous values influence the local error estimate. And so if you zoom in into this segment from 150 to 300 or so, you see it's from 100, well, let's say 100 to 350 or so. Here you see a significant error. I mean, it's the same scale, yeah, roughly speaking. But here the error only shows up at the boundary and is very close to zero, at least in the visible sense. It's and you can check here in the area of interest, in some interval of interest, maybe from 150 to 300, the error 1 is like 13% and it's 2%, so it's much better. So if you want to see how the real part of the function here, this function, you see 2 bumps and negative part here, how they contribute to the thing is, so how the convolution is realized, then you have this local reconstruction now from the green family, which again is obtained by cutting out the central part of the repetitive argument in the Fourier transform side. And you see how the amplitudes, which are just the sampling values, we could draw the curve here and say the smooth curve would go through exactly these. You need only the sampling values in order to reconstruct. And that's kind of a practical version of the Shannon sampling theorem. And as you see, it has 2 features. One is the starting point is more or less the Poisson formula. So in distributional sense, the Fourier transform of a Dirac comb is a Dirac comb. And on the other hand, the fact that convolution means periodization. And now, of course, I have other files which demonstrate that if this is maybe not perfectly band limited, so if that would be a bit broader, or if your sampling rate is too big, in our case, we have a length of 7. So I don't know, I could take, say, 480 by 7 is roughly 70. It's just violating a little bit. Then you would see even at the sampling rate of 60, everything would be fine. But maybe you go to 80, that would mean that would overlap, and the low frequency part would be fine, but you would have aliasing. So the parts from this is here. Also, the more narrow this spacing is here in the frequency domain, which means the more close you come to the Nyquest rate. The Nyquest rate is the critical distance that you would have here. The less freedom you have in choosing. So you have seen the great advantage of choosing the green window over the red window. And this would be lost if you have perfect Nyquist rate. So one should never work with the limit of a situation. And yeah, I think that's the best way to stop this part and stop the recording now first.